Yeah, hi everyone to the new video. And today we will discuss Vision Transformer, which again is like a backbone of lot of vision encoders. Almost all the vision encoders in today's time. And like we have discussed in my previous video as well for large multimodal models. Uh, One of the key component is vision encoder, right? So vision encoder has like the architecture that vision encoder has, it itself has vision transformer as building blocks. So vision transformer is also like is based on the very popular transformer architecture from the language side. So let's just start it. Yeah, so this paper was released in 2021, and the name is again an image is worth 16 cross 16 words. Transformers for image recognition at scale. Right. So, like I said, like this is again inspired from the Transformers paper, which was uh, which came in 2017, and like it completely changed the language landscape, right? The NLP landscape. So this is also based on it. And what the authors are claiming is, uh, right, in vision, attention is either applied in conjunction with CNN or used to replace certain components while still keeping their overall structure in place. But here, what they want to show is that CNN is not necessary and just a pure transformer architecture, like similar to the language one, that it can perform very well on the image classification task, right? So ultimately, there will be an image representation, right, by dense vector, and in this paper or in their research, they'll use that to classify the image, right? Yeah, and if you read this slide, inspired by the transformer scaling success in LP, uh, they will like they will try to uh, apply the transformers as it is with like very minimal modification. Of course, there will be modifications because in the original transformer, the input is a text, whereas here the input is going to be an image, right? So text is a 1D thing, right? And whereas image is a 2D, so there is a difference in that itself. So we'll see. Like I'll also break down the entire vision transformer code and yeah. So here is the uh, here is that the vision transformer. So you see here is the like the input will be an image, and the image will be split into patches. So and these patches will be arranged linearly. They will be passed into a linear projection layer. Like I will go to into the code, into the architecture in detail, but just to give you high level idea, right? And then for each of the tokens, each of the image token, you see a position embedding has also been attached with it to retain the some kind of positional information for these tokens. A special token is added here, like which is very similar to the CLS token for that image, and like serving the purpose that like this ultimately this token, like the embeddings of these token can be used as representation for the entire input, right? In this case, the image. Right, and then here is the transformer architecture, right? We get the like there is an embedding layer. In this case, the embedding patches we get which is passed. Then there is normalization, then multi-headed attention. Then like we again the original embedding is matrix will be merged again, like added to this. The attention output, then again normalization, then like MLP layer, and then again like the attention output will be merged with MLP, right? So I mean this again is like very basic. I mean the transformer architecture, the enco on the encoder side. But the main thing to notice here is like how they are using the image, like how image input is being passed, right? So, like, let's say this, the paper itself is the image, right? So they just create patches and right, and then they linearly arrange it. So this will be patch one, two, three, four, five, and then this they pass into this uh the layers. Right, we'll go to the architecture. Right, and overall, if we look at the equations, then like you see here your x would be like the first equation is nothing but it's just after the embedding layer, right? So each of the patch uh, is uh, passed to the embedding layer. So here is the multiplication, like matrix multiplication of the embedding layer with the input patches, basically the image, and then which is where we merge the positional embedding and we add a class, a special token like for that is supposed to represent the entire image, right? And then uh, which is passed through to multi-headed self-attention layer, right? And with right, so you see here, right, and with the previous attention heads output, and here MLP layer again like takes the output of attention, and yeah, yeah, we'll look into the code, right? Then it will be like very clear. Right, then yeah. So not previous layers like attention output, but previous layers output, right? Previous layer in that would be like the MLP layer. So yeah, because see there will be this is a one segment. So like initially there will be embedding layer, then there will be this block, this encoder block, then there could be multiple encoder blocks, right? But embedding layer will not be there, but this again will be like multiple uh, blocks will be there, right? Yeah, so these are the like it's pretty straightforward, right? If and now if we look at some of the results, then yeah, so this they have shown like these are like this is from the embedding layers of the transformer, right? And they uh okay, so this VIT comes in like different versions based on the size. Let me show you. Yeah, so like VIT base, large, huge, different layers, right? It depends on the different layers and parameters, right? So over here, they are saying these results are being shown for large, right? So yeah, you see different filters are obtained, are learned in through the embedding layers. So yeah, and if we look at the outputs, so yeah, so here are some of the outputs. Again, like the core philosophy or the core mathematics behind the attention mechanism is shown here, right? So this VIT was trained on classification tasks, right? So based on the classification tasks, ultimately what model learned, right? So now if we pass, let's say, this image of an owl. So if you see the enlightened circle, or if you look at the darkened circle, so less useful pixels are darkened out, right? So it will attend only to the more relevant piece in the image. So this job is done by the attention mechanism. Right. So here are a few examples that they have randomly selected. Yeah. So now maybe we can walk into the architecture VIT. So here is the code for that. I've just copy pasted it in my text editor, code editor, so that like we can just see like what are the, like we can basically investigate all the different layers as and when it's passed, right? So here is the code for the VIT. So we have a feed forward layer. Acha, let's start from VIT module, right? So here is the VIT class, and here is the forward function, and where we pass the image. Then there is something like initially, if you remember, we'll have to first do the patching of the images to pass it into the layer, because we cannot directly pass the image, right? So we'll do the patching, and here is the patch embedding layer. I'll talk about it like what it's, right. Then uh, we add CLS token. Then we what's here, like this is the special token that we add for, which is supposed to represent the image, entire image, right? Because see now, because we are creating the patches, so originally image is 2D, right? But we have colors as well. So like we can say that originally image will be represented as like height and width, and then the channel, or like, to put it simply, the value of the RGB, right? Originally image is represented like this. So now how do we pass this into our model? So we'll try to patch it, like create patches, small patches, and then linearly arrange them, and then pass it to the model, right? So these are the patches, are nothing but the image patches. So one additional thing is like that in this stage we are doing is adding a new token that's supposed to represent the entire image. Okay. So what all this would represent, all these tokens or all these patches. So in language, in text, we call it as like token text tokens, but here we are saying the patches, right? All right. So now So this is done. Then yeah, we just add the CLS token to the original our patches, right? To the original embedding token, sorry, image tokens, right? Then we add positional embedding. Then we have a dropout layer. Then we have a transformer layer. Like this is the main block, like right. So before this, like this is the transformer architecture. Again, like there will be some changes than the original transformer, like that we use in the text. This is new, right? That is completely different, which is basically for image processing. Then there is transformer layer, and then again, like there is like and it's done. Then there is nothing, right? So this is like the vision transformer module, and then we have transformer class, right? And transformer uses attention, so we have a self attention class, and we have feed forward here, right? So now let's start, right? So you see, so for just for demo, I've taken the image size to be 32. So this will be like 32 cross 32 is the image size. Channel 3, like for RGB. Batch 8, like let's say in like we in one go we are passing 8 images, right? And so I'm creating a random image. So image is nothing but numbers, right? Anything is nothing but numbers, like that can be represented by numbers, right? So yeah, so this is what I am doing. So if I print the dummy input, so what, let's see what my image is looking like. Okay, so maybe dot shapes. So basically eight with eight, this is batch size. So there will be eight image there. I'm passing eight images, and this is channel height and width, right? So eight images with uh this dimension and like this for the color information or the channel information. So this now I'll pass to the VIT. Like I'll right, and I'll create a VIT class, a VIT object. So model is like VIT model, right? Vision transformer model. So let's create this is model class, and I'm initializing it with some of the parameters, right? That it's expected, like that is defined here. So image size will be like image size, right? And patch size, uh, again like this, right? So number of classes. Okay, this is for the training part, right? Because like I mentioned earlier, like VIT was trained on classification task. So ultimately, let's say we have to classify with between 10 classes, right? So that's the 10, right? And what is patch size? Patch size is again like uh, we'll see like how it is used, right? All right. So now let's move to VIT module, right? VIT class. And initially, you see the forward method, like we pass the image to this patch embedding layer. Let's see what's doing. It's a sequential layer again, right? And the first uh, thing we notice here is rearrange, right? Like this is from this library INOPS, and it's so what it will do is let's print the dimension, right? Input uh, shape. Okay, let's remove this. So this is what our input looks like. Eight images, three rows, right? Now we are passing it into patch embedding. Let's say what this will do, right? So this will do nothing, right? So what this will do is like this is the input. It will rearrange it to this, right? So basically batch cross channel, then we have H into P1 and W into P2. this will be rearranged to batch into H into W, and we are stating that P1 is basically patch height and P2 is patch width. This we are stating here. Now, what is patch height? Patch height is basically height and width. Like if you see here, what we have initialized is we have passed this patch size, right? So we are considering again like a square patch, and patch is height and width is 4, right? So yeah. So now, if you look at the input, we know that our input looks like this 8 into 3 into 32, 32, right? So this, and we know that P1 is patch height. So P1 is patch height which is 4. So H becomes, right. So H becomes 8, right? Because this is 32 and this is 4. So H is 8. And what is W? W also becomes 8. Right. So now what this will look like is B like batch, right? Then H into W. So this will become 8 into 8, that will be 64, right? And this patch 1 into patch 2 into C. So 4 into 4 into 3. 4 4 is 16, 3 is 48, right? So this is what it will look like. What does it mean, right? Basically now from initial 8 cross, what was that? 8 cross 3 cross 32 cross 32. Now we rearrange it to 8 cross 64 cross 48. So this means like for each image and total number of patches, like for each image, for each patch, we have a representation like this is the across this dimension, right? Now we pass it to like we normalize across patch dimension layer, right? Patch dimension is nothing but the last layer. And if we look at this, so channel cross patch height cross weights, right? So across it, we are normalizing it, right? So this why we normalize like again like it's so that there is some stability like there is stability in the training, right? Then there is linear layer, right? And let's say which is taking input like which is patch dimension like 48 and output is dimension. Where is it? Okay, let's see dimension. We are passing the dimension is 64, right? So this is a linear projection, right? So then again linear normalization, right? Then again across the last layer we again normalize it. So if we rearrange it, we normalize it, then we project it linearly, and then uh, yeah. So now what should be the output after this? It would be 8 cross number of patches, right? And after this linear layer, 64. Let's print it. Yeah. So why we are doing this, right? We are doing this to prepare basically input for our embedding layer. No, so this this itself this itself is basically the embedding layer, right? This thing. right? So yeah, like in language, what we have, the embedding layer, right? It's a lookup table, right? So let's take little detour here, maybe 20 seconds, right? So embedding layer looks like there will be vocab size cross the dimension, right? So for each token in the vocabulary, we'll have a embedding representation. So here, what is the vocab, right? Right, because this is nothing but this is the input size, right? And yeah, I mean, I'm just talking like this is analogy. Anyways, let's print it. And output after. So let's go back here once. Yeah, so we are right now we are putting this part, and this part. See, it's 8 cross 64 cross 64, right? What we calculated as well. Now, we are saying like this is what the shape we have already seen, right? So B will be 8, N will be 64, and yeah. So now what we are here, what we are doing is cell.cls token. Let's see what cell CLS token is. Again, like we are creating a 1 cross 1 cross dimension. Dimension is 64, right? So a vector and parameter. So this is a learnable vector for class token, right? And we just rearrange it to be 1D. So if, sorry, we repeat it, right? Because see, our original input is a batch of images. So we repeat our this class CLS token across each image, right? And then we con add it, like we concatenate CLS with this, right? So now what happens? Our input has one more token as CLS is added. So now it becomes 65, right? So number of patches plus CLS. Now positional embedding is added, like I mentioned earlier, to retain the position of each of the patch. Right, because see, transformer, like the attention mechanism, it it attends to each and every token, right? It doesn't, like, it is agnostic to the position. So we have to embed the position information somehow. Uh, right, so where the position embedding, right? So again, like this is also trainable, and the dimension is like number of patches plus one because CLS token and dimension. This will be shared across, like these weights will be shared across all images, and then we add it to the our uh, original image tokens. So here you see, so now position is added to all the patches. Then there is dropout. Now before transformer, let's print it. So this is our size, right? So now what all things we have done? Original image we have converted, like we have created an embedding representation, and we have added CLS token. Now just pass, and after that we have also added position embedding. Now after all this, before passing to the transformer, this is how it looks. Right. Now let's quickly go to the transformer module. Now here, if you look at the forward function, there is a for loop, right, which is dependent on the layer. So like how many encoder module you want in your transformer, right? And each of those encoder module will have a attention module and a feed forward layer. And you see like this X is added, basically previous information is added to after every like this is basically this you see after embedding, and this is encoder, then this embedding vector is added to the attention output, then this attention output is added to again like the output of the MLP. Why? So again like see, while back propagating, if 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 there is loss of information, there could be, so right. It becomes, the training becomes much more stable. Now let's look at the attention module. Like let's go to this forward method, right? Let me print here into attention, and let's see what's the input. Right. Then yeah, so we have why it's printing these many times, because these many number of transformer blocks we have mentioned, like six, I think. Yeah, depth is six, you see. So these number of transform blocks will be there. And input attention, I forgot to print it. No, no, I have a print. Yeah. Yeah, so into attention, and input is like 8 cross 65 cross 64, right? So this is what is coming to attention module. Now we have QKV. So like again, like this is similar to the original attention. Like we'll have a query vector, key vector, and a value vector. Query will be like basically what we will be looking for in that patch, and key will be like what that patch will have to offer, right? And value will be like kind of like what actually it is, right? It represent what it actually offers, right? Something like that, right? So yeah, so what we are doing, right? To QQV, let's see. So this is nothing but like, a linear layer with like this is the input dimension, then output dimension. So inner dimension cross 3. What is inner dimension? Inner dimension is dimension head into heads. What is dimension head? Dimension head is 64. So multi-headed self attention, right? So there will be multiple attention heads. So 8 heads, and each of those attention head will have a right and emitting dimension of 64. So inner dimension will be like 64 into 8, and this becomes 64 into 8, 512, right? And this, where is it? The linear, where is that linear layer? QKB NN dot linear. Yeah. So this expects dimension was 64, and we get 512 dimensional matrix, right? Right. So what will happen is, we'll have a matrix which will be, let's print it, right? Q, K, P, right? And Q, K, V dot K. So this chunk will uh, split this into uh, 3, right? N dimension minus 1, right? Across, like from the last dimension, we'll have 3. So we'll have basically Q, K, and V value, and sorry, Q, K, and V. So 3 different matrices, right? And the size should be, so the input was 8 cross uh, 65 cross 64, and where is it? Yeah, so batch dimension cross 65, the token and the dimension. So 512, right? So see, this will create 512 into 3, but then again we are chunking it for, like, for 3, like for key, Q, and value. So, and yeah, so this will be a tuple, right? So let's print Q. QKV 0 dot shape. Tuple has not no object shape. What I did. QKV is a tuple. Yeah. Wait, let's just see what this is. This is the attention. All right. So this is a tuple. So we'll have length, right? If it was a tensor. So see, QKV is 3 for QK and V, and Q is, see this, right? So for each image, we'll have the image tokens or the patches, and each of those token will be 512 dimensional vector. Now, we rearrange each of them into, right, heads cross. So 8 cross 65 cross 512 to batch, like 8 cross. So this is number of heads. How many heads we had? 8 cross 8 cross n. N was like the number of patches or tokens. So 65 cross d, dimension was 64. So for each image, we'll have 8 heads, 8 attention heads, and each attention head will have, like, for each patch, we'll have 64 dimension representation, right? So we arrange it. So after this, like, what we can do is, right, across each attention head, we can have, like, different attention scores. So let's print it. Final K Q size, right? See, right? Now, here we are doing matrix multiplication of k and q and k, right? So dot product, and we are scaling it. I mean, scaling it. I mean, dividing, normalizing it. Where is self dot scale? Here you see, with 1 upon square root of dimension of head. This is very basic attention calculation, right? And then attend is here. Like, we calculate the softmax, which again, like, right. So we have, right, q t, right. So this will be like a, see. So what we are doing is, like, each of the patch, like, let's say this q, here is k 1, 2, k3, dot dot, right. Here this is q1. So this will like take the dot with all, right? And then similarly for here there will be q2 with all, right? Then we normalize it here by dimension of head, take the softmax, and then value of 1, right? So this will give us attention score, right? And across all, and then we just add it. So this will give us the representation of this patch, right, with an information across all the patches. It's a much more richer representation, right? So where is it? Yeah, then drop out. Yeah, so let's just, for the sake of it, let's print this q cross k dot shape. What will be? This will be 8 cross 65 cross 65, right? Basically for each of the tokens, so this is self attention. So for each of the token, each token will attend to every other token. So we'll have a attention score for each token across every other token. Now if you look at here, where is it? Q dot k is basically, you see, right? Then there is dropout, then output, right? Attention, again, like, multiply by v, and then rearrange it to, again, like, b cross n, like the number of tokens, and cross heads cross dimension. So this again will be print output of attention, right? Attention output. Out. Okay. So this will be b 8 cross n is 65 cross h cross d. So this will be 512. So attention will return us representation for each image 65 cross 512 attention output, you see. Now this is what attention model will return. Then we have a feed forward. So where, which will be like dimension cross MLP dimension. So ultimately here, if we print, . transformer output. So it will be like 8 cross 65, right? Like number batch size and that and MLP dimension is 128. So this feed forward layer, right? So this will be the output of transformer. Let's just comment out all these print statements, increase visibility, right? Wait. Feed forward, MLP dimension, transformer, MLP dimension. 128. Let's see. Feed forward. Right, let's see here. Right. In several layers. So each of this layer will have a attention layer and a feed forward layer. And yeah, attention is here, feed forward is here. X, the output of attention is this. Input of transformer is this. All right, yeah. So if what, let's do one thing, right? And where is attention output? Let's print that. So 8 cross this plus and input to transformer is this. So this is a matrix like 8 cross 12 size of string dimension 2, right? Maybe let's do one thing. Let's print this. Let's print here X, right? I think like this, when they are added, dot shape, yeah. Inside transformer, right? Let's do one thing. That is it. Yeah. So again, like feed forward would be dimension cross MLP. This, and we again like the input we add here. So this input is 8 cross 65 cross 64. Let's do one thing, right? Let's, yeah, ask ChatGPT. Input X and adds the original input back to it. Residual connection, yeah. But these I'm getting a little confused. So let's see. These are of different dimensions. So how are they? Right. Broadcasting a linear transformer. This also makes sense. Right. But yeah, what's the output? X to match. Right. But Y output is of X dimension on shorter dimension. Now this is fine. I mean, they are saying, so again, like this might be the implementation detail, right? Implementation once. So when we add, so there is linear projection and all. So let's do one thing. So they're saying like there will be linear transformation and all. That's fine. Right? Broadcasting and all to match the dimension. Here the output is this. Oh, let's just check the code once. Oh, right. See, I missed this. So, right, there is this dot to out, right? Where there again there is linear projection layer and output dimension is 64. Right. So attention is the output of attention will be actually here, right? And this will be 8 cross 65 cross and 64. So now they are compatible. That's what. So I got little. That's what I was wondering why it's not happening. But anyways, and similarly for feet forward. So now these are of matching dimensions, and this should be as well. Let's see where is FF in the subplot layer and feed forward. Feed forward is there up here, right? And yeah, there is layer normalization, linear, GALU, dropout, out, hidden dimension. So the output is cell dot net. What is this? And the output finally output dimension is DIM, that is again 64. So this is also 64, right? So this matches. This is the wish. And now coming back. So now we have transformer output, right? And after transformer shape, let's remove attention. Let's remove this. Let's remove this. After transformer is this, but this time it's much more richer representation. Then we do mean pooling. Like here is the pooling. We can either use this CLS token or across the last dimension of 64, we just take average, right? We do mean pooling. So ultimately the output will be x dot final will be 8 cross 64. Yeah. So this is mostly, so this is a placeholder and this is for classification. So we can skip this as well. So for any task, basically we can take this image representation and yeah, use it in different vision encoder and all. So that was all about vision transformer. Again, like this video got a bit longer. I tried to keep it short, but we got stuck somewhere. And anyways, so maybe next time I'll see that it's of more desirable size. The length is more desirable. All right, thanks.